In this video, we'll discuss the four primary transformations. Now, transformation is the change in the position, shape, and or size of a figure. We talk about the original figure, we're going to call that the pre-image, and the transformed figure will be called the image. We can label them differently to help us know which is the pre-image and the image. The pre-image will have the original letters, and the image will have an apostrophe, which we call prime. So if we think about triangle ABC as the pre-image, the transformed triangle will be called triangle A prime, B prime, C prime. Now we have three isometric transformations that we discuss. These are transformations that don't change the shape, they only change the position and location. These are the translation, the rotation, and the reflection. And it's important to recognize that in an isometric transformation, the transformed object will be congruent to the pre-image. So say we had this downward arrow. If I translate it downward, it is still congruent to the pre-image. If I rotate it, it's still congruent to the pre-image. And if I perform a second isometric transformation by translating it again, it is still congruent to that pre-image. So our first transformation we'll discuss is the translation. This moves every point on the plane a specific distance and direction. And that's important to recognize about transformations. It actually occurs to everything on the plane, but we often represent them by specific objects that have that transformation occurring. So we will look at the translation either by units being moved horizontally and vertically on the coordinate plane or by a vector that has the distance and direction for which the translation occurs. So say we have this image here, which is triangle ABC, and we have the 3 points listed to the left. And it's telling us to translate it by x minus 2 and y plus 3. This means shift the entire plane 2 units to the left and 3 units up. We represent that with the triangle by going 2 units to the left for each point and 3 units up for each point to create A prime, B prime, and C prime. And these 3 points would then be labeled as A prime is negative 1, 7, B prime would be 1, 5, and C prime would be 3, 6. Now what if you had the vector instead? Here we have vector PM. And we can see that this is moving 6 units to the right and 1 unit up. So we'd move, again, the whole plane is moving, but we'd move those 3 points, 6 units to the right, 1 unit up, and create our triangle A prime, B prime, and C prime. And we could label them as 7, 5, 9, 3, and 11, 4. Now, a translation symmetry is the idea that if we have a design or pattern in the plane, it will be infinitely translated on that plane. Now, we will only see a portion of it, kind of like this image at the bottom of our screen, but it would occur throughout the entire plane infinitely in both directions. So what we want to do is take what is given to us as a design and shift it vertically and horizontally to align it and say, does this still create the same pattern? So if we think about this pattern and trying to decide, does it have translation symmetry? We would take this 4x4 and we'd shift it to the right and say, yeah, if I keep shifting it and I align the columns, it is lining up so that they match well. And if I go downward, I can see, again, it lines up. So I continue to go to the left, right, up, and down, and I would continue to create this pattern infinitely on the plane. So this would be considered translation symmetry. Now, a reflection is a transformation that creates a mirror image of the pre-image the same distance from the line of reflection. When we think about how do we do this, we need our line of reflection, and what we're going to do is we're going to move the pre-image across that line of reflection the exact distance onto the opposite side. So say that I have my quadrilateral EFGD, and I want to reflect it across the x-axis, and here are the 4 points. So we can look at how does this change those points. So we have the x-axis here, and I want to move my image across it with the same distance. So if I think about E, it's 3 units up or 4 units up, so I'd want to go 4 units down. D is 1 unit up, so I'd want to come 1 unit down. F is 6 units up, so I want to come 6 units down. G is 3 units up, so I want to come 3 units down. And that's often one of the reasons why we do this using the axes, because it's very easy to manipulate and understand how do I create that distance. So then I would have that E would be at 2, negative 4, F would be at 5, negative 6, G would be at 8, negative 3, and D would be at 3, negative 1. And what do you notice here is that we have the same X values and the opposite Y values. So when we look at what happens across an axis, it's a little bit easier to recognize how a reflection may work. Now, reflection symmetry occurs when at least one line in a plane can split an object or a design in half such that one side is the mirror image of the other side. So we can have 0 lines of symmetry, 1 line of symmetry, or many lines of symmetry that create that symmetry of that reflection symmetry. So what we're going to do is we will draw in a potential line. We would think about how do we fold that shape and do the sides match up perfectly. So here are 3 shapes that we have. We got this isosceles trapezoid, this double arrow, and this kind of waving flag shape. If I think about my isosceles trapezoid, if I draw a line vertically, and then I'm going to take this right side and fold it backwards, what I'd see is that the two are not identical. It does not match up with a vertical line of symmetry. Well, let's try a horizontal line of symmetry. Now if I take this bottom half and I fold it upward, I'd say yes, they do align perfectly. So I'd say this has 1 line of symmetry. When I look at the double arrow, if I go vertically and I take the one half and fold it across the other half, I say yes, they actually line up. Now what if I go horizontally? If I take my bottom side and fold it upward, I say yes, it lines up perfectly. So the double arrow here would have 2 lines of symmetry. Now let's look at our flag. If I take and draw a line horizontally across the waving flag and I fold it downward, I'd say, well, no, that's not lining up. Well, what if I do a vertical line and I fold it backwards? Nope, that doesn't line up either. So this is one that has 0 lines of symmetry. Now, glide reflection symmetry is another type of symmetry that can occur. First, we need to understand what's a glide reflection. This is when we take an object or a design, we first reflect it, and then we translate it along that line of reflection. If it has glide reflection symmetry, then we know that if we take that glide reflection and continue to do it infinitely along the plane, we'll have the same shape or design. So that's how we test it. We first will take whatever we think may have glide reflection, we'll reflect that object along the line of reflection, and then translate it along the line of reflection. Say, are we still creating that same design? So what if you want to actually create one? So let's try to create our own glide reflection. What I would do is I'd take my swirl design, I'd first reflect it, and then I would translate it forward a fixed distance. And now that I have that fixed distance, I want to make sure I always follow that same distance for the translation. So I reflect back across my line and then translate it that fixed distance. And again, reflect, translate, reflect, translate, reflect, translate, reflect, translate, and keep doing that over and over again to make this design. And if I want to double check myself, I can think about the entire image, I would reflect it, and then I would translate it to the next shape to make sure that I have done it correctly and see, yes, I do have glide reflection symmetry with what I've constructed. Our third isometric transformation is a rotation, which is the transformation that turns all points on a plane about a fixed point for a fixed angle measure. So to do that, we need to recognize what's our fixed point, what's the center of the rotation, what's the angle measure for which we want to do our rotation, and then how far is each point from that center that we're going to use from the pre-image to create the image. So then as we do our rotation, make sure you maintain that given distance. Now, let's look at this triangle HKJ that we have on the coordinate plane, and we're going to rotate it about the origin. One of the nice things about doing this on the origin, keeping that distance is much easier when we're looking at these rotations about the origin because we know that it's going to flip the order of pairs every 90 degrees. And then what we have to pay attention to is which quadrant are we in. A 90-degree counterclockwise rotation of this triangle will put us in the second quadrant, and each of those signs will have an X value with a negative and a Y value with a positive. But just pay attention to the quadrant and pay attention to the signs in that quadrant. So if we want to rotate it, we can say, okay, we can flip the order of pairs, but let's look at what's visually happening. What we're doing is making a 90-degree rotation from H all the way over here, which will put H prime at negative 2, 1. We do the same thing with K. It's that same distance and 90-degree rotation over here to K prime, which is negative 3, 5. And then for J, it's the same idea. What's that distance and then the rotation down here to J prime at negative 7, 2. So we can say here is our rotated triangle H prime, K prime, J prime. Now we can have rotational symmetry as well, where this is where a shape or design in a plane creates the same shape or design when rotated about that center or that given point. And it's important to recognize that there's no fixed angle measure for the rotation, but it has to be the same throughout the entire shape. So if you have an angle of rotation of 60 degrees that creates symmetry, every 60 degrees needs to create rotational symmetry. So say you want to create rotational symmetry of 90 degrees about point A. We would then want to take our shape here and rotate it counterclockwise 90 degrees, another 90 degrees, and then another 90 degrees. And what we recognize, if we go back a fourth 90 degrees, it puts us back at the original shape. So when we think about our rotational symmetry, it is going to be some factor of 360 degrees. So if we want to then check it, let's rotate our shape 90 degrees. And we see it's the exact same thing. If you did it again, we're back to the same place. Do a third time, we're still creating the same image. And then the fourth time, we're back to where we originally started. Hence why this represents rotational symmetry. Now, dilation is our fourth primary transformation, and this is not isometric because what we're creating is a similar image to the pre-image, not the congruent image. So what we recognize here is that we have to have a center, and then we're going to create the similar image from that. So to do this, first determine your center of dilation, and then you're going to draw rays from the center through each point on the pre-image. And then we're going to use a given scale factor to create the dilated image along those rays. So it's important to recognize that often you're going to use the origin for your dilations. And when this happens, we can just multiply our ordered pairs by the scale factor to create its image. So that's an easy way to recognize how does the dilation occur. So say we want to dilate trapezoid LRQN from the origin by a scale factor of 2. And so we have our ordered pairs here. So we know that if we want to, we can just double each part of the ordered pair to create the dilated figure. But let's look at it visually as to what's happening as well. If we think about a 2-to-1 ratio, we have 3 units here. So from the distance from the origin to L, so L prime needs to be 6 units away. Hence why it's at -6, 0. When we think about what's going on with R, we draw our ray, and we're going to double that distance following that ray to get up to R prime, which will occur at -6, 4. Same thing with Q. We have our distance along the ray. We double that distance to get up to Q prime, which is -4, 6. And then for N, we're going to follow the y-axis. We're going to go from 0, 3. We double that distance, and that's why we get up to 0, 6. And there would be our dilated trapezoid.